In the hidden world beneath our feet, a drama of extraordinary proportions unfolds every moment. Here, in the damp soil and leaf litter, lives a creature so small it is barely visible to the naked eye. This is the nematode or roundworm, and one species in particular possesses a hunting skill that is truly astonishing. It is called Steinernema carpocapsae, a name much larger than the animal itself. This tiny worm, no bigger than the tip of a needle, does not simply wait for its prey to come to it. Instead, it has evolved a spectacular method to catch its dinner. It jumps. It is, in every sense, a microscopic acrobat with a deadly purpose. This remarkable worm targets flying insects, a seemingly impossible task for a creature bound to the soil. To achieve this feat, it performs a breathtaking maneuver. First, the worm raises its body from the ground, standing on its tail like a tiny cobra. It then bends itself into a tight loop, storing up energy like a coiled spring. With a sudden burst of power, it launches itself into the air. This is no ordinary hop. The worm can leap up to 25 times its own body length. For a human, that would be like jumping over a 10-story building in a single bound. It is an incredible display of power from such a minuscule animal, but the jump is even more complex than it first appears. As the worm soars through the air, it spins at an incredible rate. High-speed cameras have revealed that it can rotate up to 1,000 times every single second, a dizzying speed that helps stabilize its flight path. This spinning motion ensures it travels smoothly, turning what could be a chaotic tumble into a targeted projectile. The worm becomes a living arrow, aimed with precision at any unsuspecting insect that happens to fly past. The energy required for such a leap is immense for the worm, so it cannot afford to miss its target too often. There must be another secret to its success. For a long time, scientists wondered how this tiny hunter could be so effective. The chances of a blind jump connecting with a moving target seemed impossibly slim. It was clear that some unseen force had to be at play, guiding the worm towards its prey in midair. The answer, discovered only recently in 2025, was more surprising than anyone could have imagined. This microscopic predator has harnessed one of nature's most fundamental forces to ensure its hunt is successful. It uses the power of static electricity, turning the very air between it and its prey into an invisible, inescapable net. This discovery has opened a new chapter in our understanding of the hidden connections in the natural world. The secret to the worm's hunting prowess lies in the physics of static electricity. Many of us have experienced this force, perhaps as a small shock from a doorknob, or when a balloon sticks to a wall. In nature, this same principle is used in far more dramatic ways. Flying insects like bees or flies generate a significant electrical charge as they move. The rapid flapping of their wings, sometimes hundreds of times per second, causes friction with the air molecules around them. This friction builds up a positive static charge on their bodies, creating a small electrical field that they carry with them wherever they go. The insect becomes a flying, charged object, completely unaware of the signal it is broadcasting. The jumping worm, waiting patiently on the ground below, is able to detect and use this electrical field. As a charged insect flies overhead, its positive charge affects the worm on the ground. This process, known as electrostatic induction, causes the electrons within the worm's body to shift. The side of the worm closest to the insect becomes negatively charged, while the other side becomes more positive. This separation of charge turns the worm into a tiny magnet, with an opposite charge to the insect. An attractive force is created between the positively charged insect and the negatively charged part of the worm. It is this invisible electrical pull that gives the worm its astonishing advantage. This electrostatic attraction is the key to the worm's success. Without it, the worm's jump would be a simple gamble, with a very low chance of hitting its target. In laboratory experiments, scientists found that when there was no electrical charge, the worms only managed to land on their prey about 5% of the time. However, when they introduced a charge similar to that of a real flying insect, the success rate soared to an incredible 80%. The static attraction acts like a tractor beam, pulling the airborne worm towards the insect and dramatically increasing its chances of making contact. It transforms a hopeful leap into a guided missile attack. Scientists now believe that this entire jumping behavior would have been too risky to evolve without the help of static electricity. The energy cost of jumping is high for such a small creature, and a low success rate would mean a quick death from starvation. It is only because of the reliable pull of electrostatics that the worm can afford to take such a leap of faith. This discovery shows that animals have evolved to use the fundamental laws of physics in ways we are only just beginning to understand. The jumping worm is not just a hunter, it is a master of electricity, using a hidden force to bridge the gap between the ground and the sky. Making contact with the insect is only the beginning of the worm's journey. Once the electrostatic pull has successfully guided it onto the host's body, its next task is to get inside. The worm is a parasite, and it needs to enter its host to complete its life cycle. It immediately begins to crawl across the insect's exoskeleton, searching for a way in. It does not need to drill or chew through the tough outer shell. Instead, it seeks out the insect's natural openings, such as the mouth, the breathing holes along its body called spiracles, or the anus. Slipping through one of these unguarded entrances, the worm finally gains access to the rich resources within. Once inside the insect's body cavity, the worm unleashes its true weapon, a deadly payload of bacteria. These worms live in a symbiotic relationship with a specific type of bacteria, which they carry within their own gut. Upon entering the host, the worm regurgitates these bacteria, releasing them into the insect's bloodstream. The bacteria multiply rapidly, spreading throughout the host's body and causing a massive infection. They break down the insect's tissues and release potent toxins that quickly overwhelm its immune system. Within just 48 hours, the once healthy insect is killed from the inside out by this silent microbial invasion. The dead insect now becomes a private nursery and a feast for the worm. The bacteria have transformed the host's internal organs into a nutrient-rich soup, which is the perfect food for the growing parasite. Safe inside the protective shell of the dead insect, the worm feeds on the bacteria and the decaying tissue, growing larger and maturing into an adult. It is a gruesome but highly effective strategy. The worm does not just kill its host, it converts it into an incubator for the next generation. All the energy the insect gathered during its life is now repurposed to fuel the parasite's reproduction. After feeding and growing, the adult worms begin to reproduce, laying hundreds or even thousands of eggs within the insect's carcass. These eggs soon hatch into a new generation of infected juvenile worms. They continue to feed on what remains of the host until all the resources are completely used up. When the food is gone, these new worms, each carrying their own supply of symbiotic bacteria, emerge from the dead insect's body and disperse into the surrounding soil. They will now wait, standing on their tails, ready to leap into the air and begin this incredible cycle all over again. The discovery of electrostatic hunting in this tiny worm is a powerful reminder that the natural world is full of hidden forces and surprising connections. It is not the only creature to have harnessed the power of static electricity. Spiders, for example, benefit from this force as their webs actively reach out and attract charged particles, including pollen and small flying insects that pass by. Bees, as they fly, build up their own static charge, which helps pollen grains leap from a flower onto their hairy bodies, making pollination far more efficient. This invisible force is a fundamental part of one of nature's most important partnerships. This phenomenon, known as electrostatic ecology, is a rapidly growing field of science, revealing these connections in more and more places. Tiny flower mites, for instance, use static electricity to travel between plants. They cannot fly, so they climb to the tip of a petal and wait. When a hummingbird, with its own electrical charge, hovers nearby, the mite is pulled through the air and onto the bird's beak, hitching a ride to the next flower. Even ticks may use this force, being pulled from blades of grass onto passing animals that have built up a static charge by walking through the undergrowth. Nature, it seems, has been using this tool for millions of years. What makes the discovery in the jumping worm so important is that it reveals such a complex and dramatic use of this force in a microscopic creature. It shows that evolution can produce incredibly sophisticated solutions to life's challenges, even at the smallest scales. Understanding these mechanisms is not just a matter of scientific curiosity. These worms are already used around the world as a natural form of pest control, protecting crops from insects without the need for chemical pesticides. Learning more about their hunting behavior could help us use them even more effectively, creating smarter and more sustainable ways to manage agriculture. Every time we look closer at the world, especially at the creatures we often overlook, we find new wonders. The jumping worm story teaches us that there are entire worlds of interaction happening just beyond our senses, driven by forces like static electricity. It shows us that even the simplest of animals can be masters of physics, and that there is still so much to learn about the intricate web of life on our planet. These discoveries challenge us to keep looking, to keep questioning, and to appreciate the extraordinary ingenuity that exists in every corner of the natural world, no matter how small.